Okay, so in the last class, we have been talking about this Bode plot. So we had a discussion about this negative feedback, and then in this negative feedback, we found that there are two things that has happened when we compare ourselves with respect to the open loop system. Okay, so what has happened to the gain or the magnitude of this closed loop? Yeah, so the magnitude got decreased by a factor of this. Okay, so I think k I would have used, so I'll just use the same thing, k times that of beta. And what has happened to the bandwidth of this system when I put it in a feedback? Yeah, so this has got increased by the same factor, and this is what we have seen in the last class. Okay, so now before I proceed, I just have a simple question. If I have an open loop system, okay, having two poles, how many poles, if I put it in a feedback, how many poles we would end up having it? I have a system which is an open loop system having two poles in it, okay, and I am trying to build a closed loop out of it. Now, how many poles do I have under this closed loop system, and provided that there is no phase that is coming out of this beta? Okay, so I have the circuit and I only have this. Okay, so no phase is being introduced by this particular feedback network. So how many poles do I have in this entire closed loop system, starting with? So I just want to make a conclusion. So what I'm stating here is, this guy has two poles. Okay, now as a whole, how many poles do I have? So the answer would be 2. Okay, the same like even when we discussed about this this negative feedback, we were talking about a single pole. Okay, so we had this A of S as a single pole, and finally when we evaluated this capital A of S, we found that it also led to one single pole. And so based on this, I'm making a general argument stating that, like, how much ever pole that I have for my open loop system, even the closed loop system will also have the same number of poles. Okay, so this is based on the assumption that there is no pole introduced by this feedback network. So, okay, so with that assumption, I could be able to state. Clear? So the answer is there are two poles. Okay, so now I want to discuss about the stability. Now, in order to talk about the stability, what type of system do I generally have to look in to say something about stability analysis? Can I use an open loop system to talk about stability? There is no requirement of it, right? Okay, so in general, for what type of system then I need to look for stability analysis? Again, the other answer that I would end up having is just the closed loop system. Okay, only for a closed loop system, I want to apply the stability analysis to study about the stability of the system. Now, again, we know that there are two types of closed loop systems. One is positive feedback, the other one is a negative feedback. Now, out of these two, which one we generally go for stability analysis? Which among those systems? Negative. Okay, so it is only for the negative feedback system we go for stability analysis, not for the positive feedback, because we know that it oscillates, so there is nothing to control or something. Okay, so it is only for the negative feedback system we will go for the stability analysis. So now, having said that, so I have taken a first order system and I have put it in a kind of negative feedback, and I know that the answer of this basically happens to be something like this, right? Okay, so this is the closed loop expression A of j omega, because we are talking about frequency response, so I substitute in the place of S, I replace them with j omega, right? So after then, this is what I would have. There is one important term that I want to emphasize here. So what is this term beta times that of A? Feedback factor is beta, but we have the combination of both these things, loop gain. It's a loop gain. Okay, so we generally call the product of this beta times that of the open loop system, we call it as a loop gain. Okay, and I'm just going to denote with something like this. Okay, so this is T of j, and that is actually equal to beta times that of A of j omega. Clear? So now, in case if my open loop system had a single pole, then I can write, then this T of j omega would be returned something like beta, and this one had, okay, I'm just replacing this factor k with a naught because that would be much more appropriate rather than writing it as k. In the morning class, I just wrote it as k at the top, okay, so that's the only thing. And then here I have this P1, okay, is that is clear? So now that when I plug in here, what I would have is something like this. In the place of S, I have replaced with j omega, and then I have written down something like this. And again, I can just visually see that the product of this beta times that of a naught is again a DC quantity. So I can just label them with T naught divided by. So again, I can make one more conclusion. The number of poles that the loop gain will have again depends on the poles that I have across my open loop system. Is that is clear? If my open loop system has a single pole, then even the loop gain, even the closed loop will have a single pole in it. Okay. So now, so as I said, there is something known as, so let us assume that at a particular frequency omega equals to omega 1, okay, what happens the moment the factor, like at a particular frequency, what is happening is the product of this beta times that of a of j omega seems to be somewhere closer to the value of 1, okay, that is negative 1. What does it imply and what happens to my gain in that particular frequency? So when I plug in this particular value over here, I will have something like a of j omega of 1 divided by a 0. So what would happen actually? Yeah, so there is an infinite closed loop gain, okay, so which means that the system goes out of stability. Is that is clear? So what basically happens is like the circuit has infinite gain such that it amplifies its own noise and then starts oscillating at a particular frequency, which is nothing but at omega 1, okay. So the closed loop system will have an output that will be an oscillatory behavior, and that will oscillate or resonate at a particular frequency, which is omega 1, okay, provided if I have at omega 1 this condition. Is that is clear? And when I have such kind of situation, we can say that the system or the closed loop system becomes unstable. Clear? So based on this, I just want to derive what is known as a Barcode criteria. Okay, I think probably you might have heard about it. Okay, so before that, what is the magnitude of this? How do I write the magnitude of this T of j omega? What would be the answer for this? Yeah, it is just 1. Now what about the phase angle at minus 180 degree? Okay, so these are the information that I can directly derive from both these things. Okay, so now I'm just going to state what is known as a Barcode criteria. For a stable system, how do you define this criteria? If at all, if the system has to be stable, what is the condition that I need to place? So say for example, I'm looking at the same frequency, that is at omega equals to omega 1. If at all, if the magnitude of this loop gain becomes lesser than 1, okay, but the angle, the phase angle, so at the same frequency, it seems to be somewhere around 180 degree, which I can write it as something like beta of a of j omega 1, okay, and if, okay, so when the phase value of this loop gain is 180 degree and but the magnitude of it is less than 1, then the system would be stable. But if I couldn't be able to satisfy this, either something like this equal, or if it is greater, then the system will go into unstable condition. Is that is clear? So in order to be stable, when the phase value is 180 degree, I have to make sure that the loop gain magnitude is less than 1, and that is the criteria that we will be using for making the system to be stable, okay, if at all, if it is an unstable system. Is that is clear? Yeah. So the take home messages for stability analysis of a closed loop system, okay, it's basically enough to work. So this is one of the important statements that I would make, okay. So if at all, if I want to analyze any whether the system is stable or not, then it is not the open loop gain or it is not the closed loop gain, but what I'm really looking is at the loop gain, okay. So I will use this letter LG. So LG is nothing but the product of beta times that of the open loop system gain. Okay, so now we basically have three methods to analyze the stability of the system. Okay. So the first method is known as root locus, and the second one is the Nyquist plot, and the third one is the Bode plot. So now among these three, we will not be considering this Nyquist plot, but I will just tell you roughly what is that we are actually plotting across each of these. Okay. Now in the case of this root locus, we will be using this S plane. Okay. So I will be using this S plane, but the poles that I will be placing is not the open loop system pole. Okay. Here the poles will be the poles from my loop gain. Okay. The poles of the loop gain is what I will be using in the S plane, and we call that particular plot as the root locus. Okay. We will have some 2-3 discussion on this root locus, and the third one, which is nothing but the Bode plot. So till now we have seen that using this Bode plot, there are two types of plots that we can plot. One is the magnitude plot, the other one is the phase plot. Okay. Or we have studied the magnitude plot of open loop, and we also have studied the magnitude plot of the closed loop system. Similarly, we had even studied the phase for both the systems. But when I am trying to talk about a stability, what is it I am concerned? Is the loop gain. Okay. So in this case, in both these cases, what I do is, in the first case, in order to plot this magnitude plot, I will be using the loop gain magnitude, and that I will plot it against the logarithmic of omega, or the frequency. Okay. Whereas in the case of the phase plot, again I will consider only the loop gain, and I plot it against this logarithmic scale of this frequency. Is that clear? So for all the stability analysis, what we really wanted is just the loop gain expression, nothing else. Okay. But we will have a discussion about it, like how do we get about this loop gain. But as of now, this is the stand that I want to make you to be clear. And I also tell you one more thing. In the case of a Nyquist plot, we generally use the loop gain versus the angle of loop gain. Okay, so which is nothing but the phase. Okay, so we will be using that particular plot to study about the stability analysis. Okay, so we will not discuss about it. Okay, so what we are concerned is the first and the third one. Clear? So now let me have the discussion about the root locus of a first order system. I guess everyone knows about it, right? So there is nothing that I really need to talk. Okay, so in case if I am replacing with omega p1, it is the same thing that I am talking from before, like p1 or omega p1. Sometimes I just mix it up. Okay, do not get confused with it. Or shall I use it as p1 itself? Are you comfortable with p1? Now I will even draw the plot of my open loop. So now, how would we draw the root locus for this kind of system? I have already drawn the graph for the Bode plot, okay, where I am just plotting only the magnitude of it. Okay, just to make sure that what you have learned is what I am trying to replicate it here. Okay. As I said, root locus is nothing but I need to rely on this S plane, right? Now, when I don't have any feedback, where exactly the pole would lie for the system that I have assumed here? It would be at P1, right? So I'll just mark it here. This is the pole location when there is no feedback. Okay. Now, as I go for a feedback, how does this pole move around? Because that is what we try to learn, right? Yeah. So the pole will move towards the origin or towards the other end, like towards the negative side, the most negative side, right? So what happens is this particular pole, based on the value of beta that you have, it will be pushed towards your left hand side, okay, the most left hand side, okay, and it will be somewhere sitting here. Okay. Now, what is this location? How do you identify the location of it? P1 into, yeah, or I'll just write it in short as something like T0. Okay. So this is the root locus for this. Now, when I have a system which is having a first order pole, does the system goes out of stability? Any first order system, can it go out of stability? Why did you say that? The answer is correct, but I just want to make sure why you have told. Yeah. So one of the major factor here is all of my pole, if it is all lying towards my left hand side, then it is pretty sure that my system would be always stable. Okay. When does the system go out of stability? Whenever it moves into my right hand side. Now we'll just make a quick small exercise, but anyhow you have already answered it, but still I thought I will do it. I have two poles in my open loop system, and then I just asking you to analyze the root locus plot. How do you do that? Okay, when I have a system that has two poles, where do I place those poles first of all? Will it be automatically complex conjugate? I am talking about when there is no feedback, an open loop system. Yeah, it will be on the left hand side. Let us assume it is on the left hand side, but whether they will be on the real axis or what? Yeah, it depends is not an answer, but generally the poles will be on the real axis. Okay, so I believe if I'm somewhere wrong, you can just correct me. Okay. Yeah, zeta, but those zeta value will actually whenever you have something like a feedback, only then. But in general, when you have a passive network like RC networks, okay, so and when there is no feedback around it, they all will be on the real axis. Okay, so we assume that the system has such kind of thing. Okay, so will not much go into depth, but what I assume is like I have a pole here and I have second pole sitting here, and these are the pole locations when I have beta that is equal to 0. Yeah. So now what happens the moment I try to have a feedback? Now the point here is, what is the maximum value of this beta? 1 by? No. That is loop gain. Okay, I'm not talking about this. I'm talking about what value of beta I can hold. Yeah, that is true, but I'm talking only about beta. No, what value of beta I can hold. You see, when I say that the beta equal to 0, what I'm really telling here is that there is no feedback. Okay, now what happens the moment I start increasing the value of beta? There is some sort of feedback. Okay, what is a beta first of all? Some resistor divider, and it gives me a kind of value. Say for example, I'm trying to tap my output and I'm trying to feed a part of my output signal to the input. Am I right? So what could be the maximum feedback that I can give for it? Because obviously it is a resistive network. It's a kind of resistive network is what I'm assuming, and it doesn't provide me any kind of phase shift, resistive networks. Okay, so say for example I have a network, and you see I have this R1 and R2. If I'm tapping here, this value, say for example 1 volt, and here when I tap, I will be getting a value something in terms of decimals, right, like 0.5 or something like that, right? So I always feed back a kind of factored value of my output to the input. Clear? So what is the maximum value that I can put it back? 1, okay, which is nothing but voltage follower, right? Yeah. So there is a maximum feedback factor that I can have. Okay, beta equals to 1. So the value of beta always ranges from a value of 0, where 0 means there is no feedback, where value of 1 means a voltage follower. Is that clear? Yeah. So now let us try to slowly vary the value of beta. Now what happens to these poles? In the previous case you said that the poles will be moving towards the left, right? So now what happens for this case? Okay, say for example I have some numbers like 0.01 or something. How do they move for this particular value of beta? Okay, which one would move towards the left and which one would move towards? Will this guy go like this and this guy go like this? Huh? Okay, so P1 goes towards the left, and what happens to my P2? That also goes towards the left. I guess you said in the morning, like, you know the root locus. Okay, so what happens is, like, the P1 and P2, they actually try to meet each other. Okay, for a particular value of beta, the poles will move and then they intersect at a particular point. Okay, so let us assume that the value at which it intersects is beta 1. Okay, let us evaluate that later, but it's for a particular value of beta. Now what happens if I further increase the value of beta? Say for example, this is, say for example, it is around 0.4. Now I still have 0.6 ending, right? So right now I'm moving this value of beta to 0.5. After then, what happens to these poles? How do they move? Yeah, they cross each other and they travel like that? The system can never do that. Yeah. So one of the pole will go up, the other pole will go down. Okay, so the poles will become complex conjugate. So it is in this particular case where it turns out to be a complex conjugate. But what if I have beta equals to 0.9 or something? How do they move further? Will they travel this way or this way? So this is 1, 2 and 3. So which among these 3 paths these poles would take? Towards J. Okay, one of the answer is 1. The other answer is 3. Okay. What about the angle of departure for a 2-pole system? Angle of departure and all you would have learned when you studied about this root locus, right? So I have only 2 poles in it, and what I'm really plotting is the loop gain. Okay, how do they move? Yeah. So now these poles will generally take the path number 3. Okay. Okay, so generally these poles will move, and then one of the pole will go towards the negative side, the other pole will move towards the positive side. Okay, yeah. So now when I have a system that has only 2 poles, is the system can become anywhere unstable? Can the system can go unstable for any value of beta that I am putting? Yeah. No, because none of the poles are entering into my right hand side, right? So all the poles are staying actually in my left hand side. Okay, I guess you might be knowing, like, as I keep increasing, these poles will go towards the 0, which is somewhere at the infinity. You would have learned it. Okay, so that's all fine. So now for a system that has a single pole or a 2 pole, the system will be always stable. Okay, that is a conclusion that I can derive from both these examples. Okay, but what about a system that has 3 poles in it? And this is my open loop system transfer function, and it has 3 poles. Okay, how will I use this root locus method to identify whether the system is stable or not? So again, I'm going to use this S plane, and let us assume that the P1 is the most dominant one, and I have P2, and somewhere here P3. Okay, so these are the locations when I have beta equals to 0. Okay, now the question is, like, what happens the moment I have some beta factor? How does these poles will start moving around? Yeah, move towards 0, but those zeros are at infinity. Okay, so we don't know, but in general, how does this pole would react the moment I start having some kind of feedback, say for example 0.1? How do they move around? Okay, so one of the pole would move towards this side, the other pole would move towards this side, and what about this pole? Will it go towards the origin or towards the left? Yeah, towards the left. Okay, so this pole starts moving towards the other direction. Now at a particular value of beta, this pole P1 and P2, they intersect, right? And after the intersection, for further increase in the value of beta, they start deviating. Now how does this deviation would go? Like, will I go straight this is number 1, number 2 and number 3. So which path it would take? So Abhishek always gives the right answer. Okay, so why is it so? Number 3. The angle of departure is pi by 3 because there are 3 poles and obviously it will take 60 degree with respect to the axis of this. Okay, so what happens is like one of the pole will try to move towards this path, the other pole would go towards this path, and for a particular value of beta, okay, they might enter into right half of the S plane, and it clearly states that my system for a particular value of beta can enter into unstable. Okay, is that is clear? Now before I proceed, I want you to draw the magnitude plot and the phase plot for this type of system, so that we'll be using that particular plot for analyzing the same similar thing with respect to Bode plot, for which you need to first draw the open loop system, because that would make a sense when you when we talk about the loop gain. Okay, so the plot would be something like this. Okay, so as I said, there are 3 poles. One is this P1, P2 and P3. Now there is a DC gain, and this DC gain was at A0, and after then either you can write it in terms of dB per decade or something like dB per octave. Okay, so if it is in terms of octave, then it is minus 6 dB per octave, or you can even write it as minus 20 dB per decade. Okay. So after this, the decaying factor would be like minus 40 dB, and the third pole would induce minus 60 dB. Okay. So as I said in the morning, exactly at the pole location, the phase value would be minus 45 degree, but once you move out of this particular pole, it induces a maximum of 90 degree. Okay. Similarly, I have this at pole location P2, I have a phase value of minus 135, and at somewhere around P3, you could able to see that the phase value is minus 225. Clear? And there is also something that I have marked, which is omega 180. Okay, so it is a frequency at which my phase value is 180 degree. Clear? I'm talking about this. Okay. Yeah. So now, in the DC conditions, if this loop gain value is much larger than the value of 1, we can do an approximation, right? So what is the approximation that I can do for this A0? 1 by beta. Okay. So now I have this A0, which is nothing but 1 by beta factor, and now let us assume that the value of beta is somewhere closer to 0.1. So I'm just using some value. Okay. Now for this 0.1, I'm just trying to map over here. So this is my 20 log of A0 magnitude. Okay. Now this is a case where I am assuming that the factor of beta is somewhere around 0.1. Okay. Now what happens if the beta factor goes to 1? Where do I plot this particular line? This is the case where I am assuming that the value of beta is equal to 0.1. Okay. Now I can increase the value of beta all the way to 1, right? So I'm just assuming what happens if I have beta that is equal to 1. If that is the case, where exactly in this y-axis I will be plotting my A0 value for which beta equals to 1. Yes? So what I am plotting here is in terms of dB, right? Yeah. So what happens 20 log of 1 by beta, where beta equals to 1? Yeah? Yeah, it would be 0, right? So for a beta that is equal to 1, the baseline would be this. Okay. So it is at 0 dB, I will be trying to draw this particular line. We'll just come back to this, but as of now, we'll just talk with respect to beta that is equal to 0.1. Okay. So when it is 0.1, how will I draw this remaining graph? What did we did before? for beta that is equal to 0.1, I have a DC gain of a closed loop system, and that DC gain is somewhere here. Okay. Now I'm just trying to plot this DC gain, and once I hit this particular spot, what do I do after this? How will I draw the remaining part of my graph? What did we did before? And nobody asked question. I also went with the same flow. Yeah. Yeah. So it actually follows the open loop system path. Okay. So from here on, it just goes and follows this entire segment of it. Clear? Yeah. So now that I just want for stability analysis to plot the loop gain. Okay. I don't want anything like open loop, or I don't want anything like a closed loop, but what we wanted is a loop gain. So what is the loop gain magnitude plot? What is this T of j omega? First of all, beta times that of A of j omega. Now when I am at DC talking about T naught, what is it we are exactly talking about it? Which is nothing but the DC gain of my loop gain. Okay. What is T naught? It is beta times that of A naught, right? So when I want to plot it in terms of dB, what I am supposed to do is I need to take 20 log of T naught. Okay. So I do the same on towards the right hand side. So I would have something like 20 log of A naught times that of beta. Okay. Now how will I plot this particular graph on this magnitude plot? Is it add both? Okay, so let me further redefine this particular quantity. So this becomes, because I have a logarithm, what I can do is any product term could be written as summation. So I can write it as A naught plus 20 log of beta term. Okay. So now the addition of these two things, 20 log of T naught, I can write it as 20 log of A naught minus 20 log of 1 by beta. Is this expression is valid? I had this 20 log of beta, I wrote it as minus 20 log of 1 by beta. Is those two quantities are same or different? Same, right. What is this quantity basically? What is this quantity? 20 log of A naught is nothing but the DC gain of my closed loop or open loop. It's an open loop. Okay. What about this 20 log of 1 by beta? Not feedback. We have did some approximation, right? What is it? Is the closed loop DC gain, right? So I have a closed loop DC gain magnitude. So the only thing is, if I want to extract the loop gain, what I'm supposed to do is I need to subtract the closed loop magnitude plot from the open loop magnitude plot. So what I'm really stating here is, it is this particular portion that gives me loop gain expression, okay, or the plot of my loop gain. Is that is making sense? Are you clear with it? Okay. So what I do is I again try to draw the same picture over here. So now I just want to plot T of j omega, but this is in terms of dB. Okay. And my poles are located here. One of the pole is at P1, the other pole is at P2, and the third pole is at P3. And now I want to plot this particular graph. Okay. Now how will I draw this particular graph? Are you clear? I just want to replicate this onto my other graph. Okay. So how do I do this? What I'm supposed to do is I just take this information that I have here within this particular shaded line. Okay. So this particular shaded line I just take and then put it here. Okay. So I'll just recheck it once. It is not crossing. Okay. So somewhere you could be able to see that this particular line ends up somewhere here. Okay. So this particular spot appears between this P1 and P2. So I'm just using that particular spot and then I'm trying to replicate it on this particular spot. Okay. So I have, and this is the magnitude plot of my loop gain. Is that is clear? Okay. Now this, so for this case, this line acts as a 0 dB. Okay. As far as the loop gain is concerned, this particular line is the 0 dB line, And after then the magnitude of this is pretty simple, like you have to subtract both these things, or you need to write as something like 20 log of T naught, okay, and that is what this particular height of this particular magnitude plot. Now how do I plot the phase? What happens to the phase? And how do I relate to my Barcode criteria here? Now when I state that A of j omega times that of beta, so I am trying to read the angle. So this angle could be read just by reading at the angles of A of j omega plus the angle induced by beta, right? Because these are angles, phase angles, and when I have a product term, you can actually write it as in terms of additions, okay? Now, how much is the phase contributed by this beta? 90 degree? It's a pure residue network is what I was keep telling. Do you remember at the beginning of the class I said, yeah, so there is no contribution from here, okay? Because the assumption that we made at the beginning was that the beta or the feedback network doesn't introduce any sort of phase, okay, between the input and output. So what I can do is, whatever the phase value that I had for this open loop, I can use the same, okay? Okay, so just because this beta doesn't introduce any kind of phase, I can actually neglect just because it actually gives us zero phase shift. So I'm not going to consider. So whatever the phase value that is introduced by this open loop gain, I can use the same plot, okay? So I'll just switch back here, okay? Now the point is, for a feedback network, having this as its feedback factor, that is 1 by beta, okay? Is the system is stable or not? I have 3 poles in my system, and I just want to know that I have chosen a value of beta here, okay, such that I have this closed loop somewhere here, okay. Now the question is, how do I analyze the Barcode criteria and then see whether the system is stable or not? How do I do that? What is this Barcode criteria states? Okay, the magnitude of my okay, yeah, so the magnitude is supposed to be less than 1 when I have a phase value of the loop gain at 180 degree, okay, and that is the thing. There is also one more way by which we can see it. We just see this is my 0 dB line for my loop gain, okay. So this entire curvature or this entire box is my loop gain, and this is the 0 dB line for me for the loop gain, okay. At 0 dB line I have a gain of 1. At this value of 1, when I see what is my phase value, it is just 90 degree. Now, is the system is stable or not? Yeah, at 180 degree. Yeah, that is for sure. I can also talk with respect to the place at which I have the magnitude of my loop gain is 1, and I am looking for the frequency. So when I look for this frequency, I should not have a phase value of minus 180 degree or more, okay, more in the negative direction, okay. So in this case, I have a phase value of this particular loop gain, which is basically minus 90 degree, which is less than my 180 degree, okay. So which means that the loop will never become positive feedback. Is that clear? Does this make sense? Yeah. So this is one way of looking at the circuit. The other way is to see, say for example, I have some frequency omega 2 at which I have the magnitude of my loop gain is equal to 1, okay. At that particular frequency, I have to make sure that the loop gain phase value is, I think I should write it as greater, right? This is also true, right? So when I have minus 90 degree, which is bit greater than this minus 180 degree, the system will not form a kind of positive feedback. It will stay as a negative feedback, okay. I can also state the Barcode criteria the other way. I am looking at the magnitude and see at what frequency the magnitude of the loop gain is becoming 1. okay, and in that particular frequency I'm looking for the phase value. If the phase value is greater than 180 degree or greater than minus 180 degree, then the system is stable, okay. But in case if it is equal to 180 degree or minus 180 degree or less than minus 180 degree, then the system becomes unstable. So in this case I have a value of minus 90 degree which is satisfying this first criteria, okay. Minus 90 degree is greater than minus 180 degree. So in a way the system, when I have formed a feedback with a value of beta that is equal to this, then the system would be a stable, okay. But what would happen okay, so I have connected a new feedback whose value is beta 2, okay. So now based on this I am trying to draw the closed loop magnitude plot, okay. So this would create a kind of graph something like this, okay. Now how do I extract the loop gain for this particular new value of beta? Yeah, so I have to subtract this open loop from the closed loop, right? So okay, so for this particular value of beta, okay, I have this closed loop and then I have to extract this entire shaded portion as my loop gain, okay. So now how will I see whether the system is stable or not at this particular point, like for a value of beta that is equal to beta 2? Can you tell me if the system is stable? How do I measure it? So I know that this is my 0 dB line for my loop gain, okay, and that is intersecting at a particular axis or at a particular point, and this intersection gives me a value of omega, okay. At that particular omega, when I see here, I have a particular value for a phase, right? What is that value? It is almost closer to minus 180 degree. Now is the system for this particular feedback factor, is it stable or not? Marginally stable. Now if I go for a higher value of beta, okay, so when I say beta 1, beta 2, beta 3, I am all the way shifting the value of my beta from 0 all the way I am getting closer and closer to the value of 1, okay. So now I have this new value of beta, okay, so which I label it as beta 3, and for this I am just trying to draw this closed loop. How do I extract the loop gain from these two plots? This is my open loop, okay, and this is my closed loop. How will I extract? The difference of these two magnitudes would obviously get me the loop gain, right? Yeah. So now we know that for this particular loop gain, this is my 0 dB line, and this 0 dB line is intersecting my original graph at a particular omega, okay. So now at this particular omega, when I go and see what is the phase value, I am getting a value that is much smaller than the value of 180 degree or minus 180 degree, okay. So which is almost like minus 230 or 250, right? So at this particular phase value, my system enters into unstable, okay. Is that all clear? I don't know how many people have remembered those statements. I always tell, like, the worst case condition is having a beta that is equal to 1. Do you remember that when we discussed about some of the concepts? I said the worst condition would be having a value of beta that is equal to 1 and the voltage follower is such kind of configuration, okay. So now that you are being asked to design an op amp, okay, and we know that this op amp has 3 poles in it, 3 or 4 poles, okay, but what is the feed, and you have given this for a commercial purpose, okay, and the guy like me, I can have a beta factor that is equal to 0.1, or even I would even have a feedback factor which is equal to 1, which is nothing but a voltage follower. Under such condition, the feedback, if the gain of my system is, if the open loop gain of the system is having such kind of structure, then what would happen? What happens? I would be thinking like I will get a kind of whatever the input that I am giving, I would feel that the same kind of output would appear, but rather it would be totally different, okay. So we know that a system having 3 poles, obviously it will end up having an unstable condition, but we can actually engineer those particular poles in such a way that whatever the type of feedback that your design has, still we can make sure that the system will be always stays in the stable region. Okay, and regarding that we will talk about it in the next class. Is that clear? For the system that I had written down, this will not work for a feedback factor that is greater than beta 2. Okay, after then the feedback would change into what is known as a positive feedback, and the output will keep oscillating. Okay, so this is not suitable, but I want to design a system for whatever the beta factor that I plug in, I need to always have a negative feedback around it. Okay, so that is the motivation for our next session. So with that we'll complete.